So, in continuation of our mole concept, we have so far discussed about using the formula or using the conversion factor between moles and mass. So that is mass upon relative atomic mass or relative molecular mass or relative formula mass. It depends upon the type of question given. If it is talking about an atom or an element, then we can work out or we can use atomic or relative atomic mass. If the question talks about a certain covalent bond or a covalent compound that usually have a molecule inside them, so then we can use relative molecular mass, or if the compound given or the question relates to the ionic compound, then we can use accordingly formula mass or relative formula mass. And all these three, they can be calculated using the knowledge from the periodic table. And we have attempted certain questions again related to the above formula given. Now there is one other concept or one other formula that we usually use to calculate moles, that relates number of particles. So that is basically number of moles is equals to number of particles divided by Avogadro's number. Amedeo Avogadro was a scientist who calculated the number of moles or the number of particles in 1 mole of a substance, and he rounded that up to Na, that is 6 exponent 23 particles makes up 1 mole. So if we are working with this formula, we can again use the concept of atoms, compounds, or molecules and ions basically. So let's study a question. Maybe a question can be something like this: calculate the number of moles in 24 atoms of carbon. So how would we solve this? It's really simple. It says there are now 24 atoms. So I can use the formula n is equals to number of particles. Now number of particles may be replaced by number of atoms divided by Avogadro's number. So using Avogadro's number, that is 6 into 10 with power 23. So n equals number of atoms. Number of atoms are 24 divided by 6 exponent 23. So this becomes 4. So the answer is 4 into 10 with power minus 23 moles. A question can be shifted in another pattern, like calculate the number of particles or number of molecules in 2 moles of, let's say, water H2O. So again, now we can use the same formula. N is equals to number of molecules, since question refers to molecules, divided by Avogadro's number. So we are having 2 moles here. So this is 2. Number of molecules are unknown, divided by Avogadro's number. That here is 6 into 10 with power 23. So this is when this shifts to left hand side, this gets multiplied. So it is basically 2 times 6 times 10 with power 23 is number of molecules. So then it becomes 12 into 10 with power 23 molecules are there. So another category of the questions can be, a question may work out or may ask, what is the mass of 100 formula units in calcium carbonate. So this is a bit tricky question, but if you know these formulas, n is equals to mass upon relative formula mass, or n is equals to number of, now this would be ions or formula units upon Avogadro's number. So this can be easily worked out. For instance, I know these 100 formula units are given. So this is 100, this I know. Then I can calculate moles, and using the concept of then moles multiplying by the relative formula mass, I can work out mass. So let's do it. N is equals to number of formula units, they are 100 over 6 exponent 23. So 100 divided by 6 is 16.6. So N is 16.666. So we can round this up to 16.67 exponent minus 23. So using this formula, we get this. These are basically number of moles. So now if we know moles, we can use the formula here, that is 16.67 exponent minus 23 equals mass upon relative formula mass. Now for CaCO3, we can work this thing out like CaCO3, calcium atomic mass 40, number of atoms 1, 40, carbon 12, number of atoms 1, 12, oxygen 16, number of atoms 3, so this is 48. So we get 100. So this is 100. Basically use here, so this becomes 100. So 16.67 exponent minus 23 times 100 mass. So 16.67 minus 23 and 100. So this becomes minus 21 grams as mass. So this is these basically three questions would help you understand the entire concept of stoichiometry, and then we can use obviously the same for concepts and working out chemical equations, but we need to move on gradually and step by step. Okay. So now the other formula or the other concept related to mole is number of moles can be calculated by using the volume of any gas. So the formula is now volume. This basically is in cubic decimeters, or sometimes also known as liters. See, this needs to be kept in mind that whether you use volume in liters or cubic decimeters, it's the same thing. They are not certain different units. They are the same terminologies of the of interchangeably that is basically used. Divided by 22. So when you're using this formula, you need to be cautious, or you need to take care of using proper units. If question talks about the volume of a gas in milliliters, let's say, so using the appropriate division, you can work out the conversion from milliliters to liters, or it may say gas has a volume in certain cubic centimeters. So then again you need to calculate, or you need to convert these two into liters or cubic decimeters. Then, for example, question says, what is the volume of 2 moles of carbon dioxide? So I can use the formula given, that is volume over 22. This is standard molar volume, that is the volume occupied by 1 mole of any gas at standard temperature and pressure. By standard temperature and pressure, we mean at 273 Kelvin and at 1 atmospheric pressure. So this constant is derived on the assumption that my gas, that any gas would occupy a volume of 22 liters if it has a if it is having 1 mole at standard conditions. So I can use the formula here. I can find N as 2. I don't know volume and this is now 22. So 22 times 2 is 44 what liters. This needs to be kept in mind clearly. So 44 liter or volumes of carbon dioxide would be having occupying 2 moles in certain stoichiometric analysis. Now even we can merge all these formulas into a single question, such as question says something like this: methane burns in air to form carbon dioxide and water. That's the equation here. It may ask us what volume of carbon dioxide will be produced by 100 grams of methane. Part B may say what moles are produced by what moles are produced by 100 grams of methane. So this is what moles of oxygen, or it can be water H2O. What moles of water are produced by 100 grams of methane? And okay, let's find. Let's keep it clear. So how do we solve this? First, we need to consider form an equation. Methane is CH4. It burns in air. That means it is reacting with oxygen. It forms two products, carbon dioxide and water. And then we need to see whether this equation is balanced. So just giving a check that is it balanced. So carbon 1, carbon 1, hydrogen 4, hydrogen 2, oxygen 2 and oxygen 3. So not balanced. So then I need to balance it up. So balancing. This becomes CH4, this becomes 2 moles of oxygen, then CO2 with 2H2O. Now it appears balanced, right? So now these coefficients here in stoichiometric analysis, they are basically interchangeably used by moles. That means I can read this as, there is nothing written here, so this is 1 mole of methane reacting with 2 moles of oxygen to produce 1 mole of carbon dioxide and or along with 2 moles of water. Fine. So this red lines, they basically would now be meant to be replaced as moles. Then if we work out part A, we can identify what's given and what's required. So I do make this habit of underlining my keywords in the question. It says what volume of, so volume of CO2 is required. I'm sorry, this is not given, this is required. So let's change this given to required. And then what's given in part A is 100 grams of methane. So required here is volume of carbon dioxide and given here is 100 grams of methane. So 100 grams of methane given. So how would we proceed? See, I can relate this to my question. Equation is considering or is having 4 basically compounds, but The part A is referring to methane and carbon dioxide only. So according to the question here or part A, I can simplify this. So it says on the reaction side, 1 mole of methane is producing 1 mole of carbon dioxide. So the idea is now I can neglect oxygen and water because part A is not talking about oxygen and water. It is only talking about methane with carbon dioxide. So what I'm given is with 100 grams of methane. So but it is 1 mole here. So now I need to convert this mole into grams. How can I do that? We just learned that in the previous calculations. So we can proceed accordingly that in order to convert moles to grams, what do? We multiply moles with molar mass or relative molecular mass. That is 16 in case of methane. So 16 grams of methane gives 1 mole of carbon dioxide, and again required is not moles, it is basically volume. So now I can convert this mole into volume according to the calculations that we just learned previously. So this is 1 times 22 liters of carbon dioxide. So I can repeat this. See, this 16 is basically the relative molecular mass of methane gas. So why am I multiplying this 16 with 1? Because this is number of moles, this is mr. So according to the formula, n times mr equals mass. Same goes here. This is n, that is number of moles. This is standard molar volume, that is 22, that we just learned. So 1 times 22 is basically what? Is basically the volume of carbon dioxide. So now my question gets simplified as 16 grams of methane gives 22 liters of carbon dioxide. So if I am working with these values, now I need to just simplify this 16 to 100, as now it can be worked out by any mathematical calculation you are interested in. You may use by proportional analysis, you may work out the stoichiometric analysis. What I would do is I would divide both the sides with 16, that is 16 over 16 grams of methane will give 22 upon 16 liters of carbon dioxide. So this becomes 1 gram of methane gives 22 divided by 16 is 1.375. So it can be approximated as 1.4 liters of carbon dioxide. So now I can multiply this with 100. So this becomes 100 grams of methane will give, this is 1.4 times 100 liters of carbon dioxide. So I can proceed accordingly. This is 100 grams of methane will give 140 liters of carbon dioxide. So what I have used is I have divided 16 with 16 in order to make this 16 1. When I know 1 gram of methane gives this much liters, I can calculate liters of carbon dioxide by any given gram of methane. I hope this video clears your concept about stoichiometric analysis. Now coming towards part B, it says again the same procedure given and required. What's given in part B? 100 grams of methane. So mass of methane is given, 100 grams of methane is given in part B, and what's required in part B is uh, mm, what moles of water. So okay, number of moles of water are required. Moles of H2O are required. So again, I can proceed accordingly. In the given question, I need to work out methane with water. So I can see I can neglect or I can totally ignore oxygen and carbon dioxide in part B. So I can now write 1 mole of methane produces 2 moles of water. So again, by using the same process that, as utilized here, I can directly now write simplify 16 grams of methane gives, this is 2 moles of water already. So that's okay. Now I don't need to convert this moles into anything as my requirement is of moles. Now I only need to convert this 16 to 100. So according to the same approach that I utilize or explained you guys previously, this can be divided by 16. Same goes for here. This can also be divided by 16. Then it becomes 1, and then 1 times 100, then the same thing times 100. So I can write directly 100 grams of methane will give, this is 2 over 16 times 100 moles of water. So I can have my answer as 100 grams of methane gives 12.5. You can simplify this moles of water. So by using the same tools, we can work out any possible calculation of a stoichiometric analysis. Okay.